As we've all heard before, coronary heart disease is one of the leading causes of death, accounting for 1 in every 6 deaths in the US. And this prevalence, as well as fiscal impact, is only going to increase as we're able to live longer. So what is coronary heart disease? Well, up there, that's a coronary artery, and when it becomes blocked, it causes the surrounding tissue to die, which impedes the heart's ability to adequately pump blood, the blood that's critical to our survival throughout the rest of your body. Despite years of research, why are these cardiovascular incidences, as well as their subsequent mortality rates, still so high? Well, let's look at our treatment options. First, we could take medication that would reduce the demand of nutrients to the heart and may prevent the disease from progressing. Or we could take a vascular surgery, which would circumvent the occluded area and possibly prevent a second and third heart attack. But neither of these solutions adequately replaces what's already been damaged. And what most people don't realize is that unlike your skin, your heart cannot regenerate. That damage is permanent. So if you want to adequately replace that damaged tissue, you're going to need a whole heart transplant. And this is both very invasive, and also there's a huge organ shortage, and the wait could be up to 400 days. So ideally, we'll be able to build a patch that will replace just the damaged portion of the patient's own tissue. Now, to build a heart, it might seem, it's a little bit more complicated than it seems. So first, you have to take a stem cell and drive it into a cardiomyocyte, because again, these cells don't regenerate. Getting from a cadaver or living donor is not a viable option. And second, once we have those cells, we have to form them into a 3D tissue. And this is in order to get the cells-to-cells communication going, as well as the nutrient transport. And we also know this because we found that when researchers injected cell clusters into hearts, there was only moderate improvement. So it seems like this is a key step in the process. And third, we need to train our 3D tissue so it's ready when we implant it into the heart. So to do this, we make a little gym and we stretch it so that it will be completely exercised and ready for when it's moved into the heart. So in my lab, we've been working on addressing each of these issues. So here on the left, you can see cardiomyocytes, or heart cells, that I derived from stem cells. In the middle, you can see a barrier where beads are flowing through. That's my 3D tissue tube. And on the right, you can see the tube, and it's undulating and being stretched. And hopefully, the next step will be to put it into a heart. Thank you.